Okay, so we're going to talk about organometallics. So organometallics are really important. So back in the early 1900s slash 1800s, they were basically just giving out Nobel Prizes for people who could make carbon-carbon bonds, right? Grignard, Grubbs, Heck, Suzuki. You guys didn't really learn about Heck and Suzuki, but you know Grignard's reagent. Oh, I guess you didn't learn Grubbs either, but you know Grignard, right? So he was one of the first people to figure out how to make carbon-carbon bonds. So typically speaking, carbon bond polarization is as follows, right? We usually have a Z that's more electronegative. So this is a partial positive. Nucleophile comes here, kicks this off. We have this group. However, an atypical carbon bond polarization is what we get in organometallic compounds. It's a compound that contains a carbon metal bond. It also can contain like a carbon metalloid bond, boron, tin, some transition metals, whatever. For the purposes of this class, it's a metal. So this actually means that the C is a partial negative and the M is a partial positive, which makes this a nucleophile attacking an electrophile versus we saw here a nucleophile attacking an electrophile the other way. Cool. So many metals can form bonds with carbon. These are some of them: Mg, Li, Cu. Those are probably the ones that you recognize. Pb, Ru. So the magnitude of the minus is determined by the electronegativities of the particular atoms. So the partial negative in the carbon determines how reactive the organometallic compound is, right? So look at the periodic table. The greater the polarity of the carbon metal bond, the more reactive the compound is. So the greater difference in the electronegativities, it would make sense, right? It would be more electronegative. It would be more reactive. So CH3Li is more reactive than is the more reactive carbon metal bond when compared to CH3Mg. And you might be like, oh, isn't MgBr Grignard's reagent stronger? It is. We haven't added the Br yet, so don't worry about that yet. Organolithium and organonesium compounds. So organolithium compounds have a CLI. So the way you prepare it is pretty easy. You start with an alkyl halide, you add two equivalents of Li in hexanes, nonpolar solvent, and you get this alkyl lithiumide. It's not an SN2 reaction. You're not on the hook for the mechanism, so let's not worry about it. We can also use this with aryl halides. This is very important that we can use this with aryl halides. Okay. Organomagnesium compounds. Okay, it was just spelled wrong. My bad. I don't know what I'm doing. Organomagnesium compounds have a CMG bond. So the way we prepare it, we start with an alkyl bromide, and we actually insert the Mg within the Br, right? As opposed to this one, we just put an Li on it. Interesting. Mg in ethers, we make MgBr. It also works with aryl halides. Why do we use an ether solvent? This is why I'm not going to go over it because it's not really that important, but if you're interested, you can probably look it up and find some videos on it pretty easily. Okay, substrate scope for organolithium compounds. Alkyl halides, aryl halides, vanillic halides, halogens. Usually Br, but it can also be Cl or I. Practically speaking, we use Br because it's a combination of fast and inexpensive. Iodine is actually really expensive. In practical organic chemistry. But for our purposes, we don't care about that, right? Okay, reactivity. Both organolithium and Grignard reagents act as nucleophiles, right? We treat them as partial minus, partial positive, so we can effectively treat it as a carbanion. It's not exactly, but it's pretty much that, right? So we can think of it as this when we're talking about like reactivity, reaction mechanisms, modes of reactivity. So both of these are very strong bases, right? Because they have a negative. So let's go back to epoxides, right? So in basic conditions, the attack of the epoxide is on that of the less substituted side. This side is symmetric, it doesn't matter, but remember, like, it's negative, so we treat it in basic conditions. And then we have to do a workup step because since we're in basic conditions, we will never have a group protonated. Because remember, in basic conditions, there's always a minus or neutral. We never have a plus or a proton in general. Acid-base chemistry always occurs faster than any other type of reaction. That's why we have two steps here. Okay. Mechanism of formation, knowledge of the mechanism is not required. It goes through a radical reaction. Utility of organolithium magnesium. So this method actually allows you to invert the reactivity of compounds. So this is a trend that we get a lot in organic chemistry of turning an electrophile into a nucleophile. And because of that, we have suddenly elevated the different ways they can react in. Limitations of the methodology. Organolithium and organomagnesium compounds are incredibly strong bases. They cannot be prepared from compounds with acidic groups. because what will happen is they'll just deprotonate the acidic protons, right? So if I put a minus here, this minus is going to come here, kick off this, and it's not going to be very useful, right? So the reactions also have to be kept free of water, even trace amounts. So this is really important, especially in practical organic chemistry. So we get a lot of side reactions. And safety procedures, I mean, Li, alkyl lithiumides, I don't know, I should figure out what that is. React with H2O and air, they're pyrophoric, they're just really bad. Okay, they're just dangerous. Limitations of the methodology. Organolithium and organomagnesium compounds are incredibly strong bases. They cannot be prepared from the compounds with acidic groups. Reactions must also be kept free of water, even trace amounts, dangerous to handle without proper safety procedures. They will not participate in substitution of alkyl halides. Okay, cool. This is important. Not participating in the substitution of alkyl halides. Think about for a second why that is. This is because they act as bases and they do elimination reactions instead, right? Secondary position elimination is preferred. So we'll just get this as our major product over this. It'll still be a reaction, but not really what we wanted. The only caveat to this is aromatics. So again, resonance is always the caveat. It's always the exception. So if they're primary benzoic or allylic, then we can get reactions of alkyl halides. And that's just because we can't do an elimination because the elimination is, to make a double bond or to make a benzene. It's already happened. We can't do that. So we will get the products that we would generally expect. Okay, organocuprates, they're a coupling reaction. They form carbon-carbon bonds with the transition metals. Gilman reagent, this is a type of organocuprate. This is the particular organocuprate that you will be using within the context of this class. So the way you prepare it, 2 equivalents of Li in hexanes, nonpolar solvent, we get this, 2 equivalents. CuI, THF, transmetallation. So this is basically we're installing a metal between these two. And now we have CuLi, we have the Gilman reagent. Okay, this is less reactive than RmGbR and RLi. The change in electronegativity between them is smaller, it's less basic, and it can do substitution reactions. So you don't really see it doing eliminations, right? So this is one of the differences between Grignard and Gilman. This is like a little bit weaker nucleophile, weaker base means, prefer substitution. Weaker base means I prefer substitution. Okay, substitution reactions with the Gilman reagent. Exactly what you would expect. Make sure that 1, 2, 3, 4, the carbons in here are the number of carbons you add. 5, 6, 7, 8, 5, 6, 7, 8. CuLi outside, 2. We need 2 equivalents, or we need a subscript 2. That's very important too. This is unreactive. We don't need to know these mechanisms. We can, for the purposes of predicting products, you just treat it as a minus. Okay, scope of organocuprates. The alkyl group of the organocuprate and the alkyl halide can be an alkyl group other than the secondary, unless it's a cyclic, primary will work, or tertiary, alkyl will never work. Okay, so I'm not going to go through these specifically, but you can look through these and, it's basically based on the trends that we just talked about. This is styrene, full compound. Substitution with Gilman reagents is stereospecific. So avoid manipulating the starting materials. We invert RNS. Well, yes. Anyway, what this is saying is this is showing double bond things, and we're showing how cis goes to cis, trans goes to trans. I think this note here was just the same thing happened for RNS, and I believe it does. Okay, organocuprates as nucleophiles. Again, we're installing this basic conditions. We attack this side, kicks up. So that makes sense. I don't know why I drew the arrow here, but anyway. Okay. Bulky bases minus CH3. Well, the base will, since it's basic, it'll have to attack the less sterically hindered C of the epoxide. Exactly what you'd expect. Everything else is stuff that we covered last year, but we didn't get to this year. So yeah, I mean, I'll scroll through and you can pause and read if you're interested, but it's not relevant to the class you're taking right now. So